1 in 16,000. That is the probability that the result is noise. That is the probability that 650 billion particle decays, analyzed over years with the most sophisticated detection equipment humans have ever built, produced a 4 sigma deviation from theoretical prediction by random chance alone. 1 in 16,000. Not a definitive discovery, but not nothing. Here is what happened. Physicists at CERN's Large Hadron Collider spent years studying an extraordinarily rare event called a penguin decay, in which a beauty quark transforms into a strange quark. For every million B mesons that decay, only one decays this way. The rarity is the point. Rare processes are uniquely sensitive to disturbances from unknown physics operating at deep levels. If something undiscovered is influencing the fundamental behavior of matter, it shows up in these rare decays before it shows up anywhere else. Researchers analyzed hundreds of billions of these events and found that the results did not match what the standard model predicted. The deviation measured 4 standard deviations from expectation. In particle physics, 5 sigma is the threshold for an official discovery claim. 4 sig. Ma is the threshold for a serious problem. The standard model has stood since the 1970s. That is not a trivial statement. In 50 years of experimental physics, at accelerators of increasing power, with detection instruments of increasing precision, across thousands of independent experiments conducted by thousands of independent research teams, the theory has held. Every prediction has come back confirmed. Every number has matched. It is the most precisely tested theoretical framework in the history of science, and it has survived every challenge thrown at it until physicists started looking carefully at penguin decays. What does a 4 sigma deviation actually mean? It means that if the standard model is completely correct, and if you ran this experiment over and over again, you would see a fluctuation this large by chance alone, roughly once in every 16,000 tries. That is not a comfortable number. It is not comfortable in the way that 1 in a billion would be comfortable, where the noise explanation is obviously right. It is not comfortable in the way that 1 in 5 would be comfortable, where no serious researcher would treat it as significant. 1 in 16,000 sits in the range where the field cannot dismiss it and cannot yet confirm it. The tension is deliberate. The data is forcing physicists to sit with an answer they are not yet authorized to give. Now consider who was looking for this. Particle physicists have not spent decades building increasingly powerful accelerators because they were confident in their theory. They built them because they knew the theory was incomplete. The standard model does not include gravity. It says nothing about dark matter. It has no explanation for why the universe contains matter rather than equal quantities of matter and antimatter that should have annihilated each other after the Big Bang. The theory that governs everything physicists can directly observe accounts for roughly 4% of the universe by mass and energy. The other 96% is not in the equations. Every physicist working at CERN already knows the model is not the final answer. What they have been hunting for is the furs. The experimental signal that points toward what the final answer might look like. That is what a 4 sigma deviation in penguin decays could be, not the answer. The first crack through which the answer might eventually become visible. William Barter, a particle physicist at the University of Edinburgh who works on the LHCb experiment, described this result as among the most significant findings of the last several years at the LHC. That is a considered statement from someone inside the field, and it means something specific. It means the result is not being quietly set aside. It means the theoretical implications are being taken seriously. It means the question of what produced this deviation, whether it is an unknown particle, an uncharted force, or something that does not yet have a name in the theoretical literature, is now a live question rather than a speculative one. If the standard model is wrong or incomplete in the direction this deviation is pointing, then the particles and forces described by 50 years of confirmed physics are not the bottom of the structure. Something else is underneath, and whatever that something is, it operates at scales and in ways that the current framework cannot describe. The history of physics says that when the deeper layer is finally exposed, it tends to be stranger than the layer above it. That pattern has held from classical mechanics to relativity to quantum field theory, and there is no particular reason to expect it to stop now. 1 in 16,000. And that number is the most dangerous thing particle physics has produced in 50 years. The standard model describes how everything you have ever touched, seen, or interacted with is built from a small set of fundamental particles governed by 3 forces. That is a remarkable claim. it is also accurate. Start with the particles. Matter, at its most fundamental level, is made from two families. Quarks are the building blocks of protons and neutrons. 6 types exist: up, down, charm, strange, top, and bottom, and they combine in different arrangements to produce the particles that make up atomic nuclei. You have never seen a quark in isolation. They bind together through the strong nuclear force with such intensity that separating them requires enough energy to produce new quarks instead. The universe does not permit them to exist alone. The second family is leptons. The electron is the most familiar. Leptons do not feel the strong nuclear force. They interact through electromagnetism and the weak nuclear force, and the electron's electromagnetic interaction with protons is what holds a toe misses together. Without that interaction, every atom in your body disassembles instantly. Then there are the force-carrying particles called bosons. The photon carries electromagnetism. The W and Z bosons carry the weak nuclear force, responsible for certain forms of radioactive decay. The gluon carries the strong nuclear force, binding quarks inside protons and neutrons. The Higgs boson, confirmed at CERN in 2012 after a 40-year search, gives other particles their mass. That is the complete inventory. 12 matter particles, 4 force carriers, and the Higgs. Now consider what this model has actually done. It predicted the existence of the W boson and Z boson before they were found. It predicted the Higgs boson decades before the technology existed to detect one. It has calculated the magnetic moment of the electron to 11 decimal places, and experiments have confirmed that calculation to 11 decimal places. That level of precision has no parallel in the history of science. No other theory built by human beings has been tested this rigorously and come back this consistently correct. When physicists call it the most successful theory ever constructed, that is not sentiment. It is a statement about the numbers. And here is where the problem begins. The model accounts for 3 forces. The fourth force, gravity, is not in it. This is not an oversight. Gravity has resisted every attempt to integrate it into the framework. General relativity describes gravity as the curvature of space-time produced by mass. The Standard Model describes the other 3 forces through particle exchange. These 2 descriptions are mathematically incompatible at the scales where both should apply, and no one has resolved that incompatibility in 50 years of trying. What the model also does not contain is dark matter. Galaxies rotate at speeds that require far more gravitational mass than their visible stars and gas can produce. Something is providing that mass. It interacts gravitationally, it does not emit light, and it does not appear anywhere in the Standard Model's particle inventory. Dark energy is similarly absent. The repulsive force driving the accelerating expansion of the universe has no mechanism in the model at all. Add those numbers up. Visible matter, everything the Standard Model describes, constitutes roughly 4% of the universe's total mass and energy content. Dark matter is approximately 27%. Dark energy is approximately 68%. The theory that has predicted experimental results to 11 decimal places has nothing to say about 96% of what exists. This is the structural tension at the core of modern physics. The model works with extraordinary precision inside its domain. Its domain is a small fraction of reality. Physicists have known this for decades. The hunt for something beyond the Standard Model, for the theory that extends it, replaces it, or absorbs it into something larger, has been the central project of high-energy physics for a generation. The anomalies in the penguin decay data are not interesting because they are surprising in isolation. They are interesting because they may be the first measured signal of what lies outside that 4%. The most precisely tested theory in the history of science accounts for 4% of the universe and has nothing to say about the rest. The name comes from a physicist's joke about a Feynman diagram that looked, with some imagination, like a penguin. The physicist was John Ellis. The year was 1977. He lost a dart game. The penalty involved drawing a penguin on a blackboard, and the shape of the diagram suggested the name. That is the full origin story. It is not a serious name for a serious process, and yet the process it describes may be the most consequential thing happening in particle physics right now. What a penguin decay actually is requires understanding one thing first. Quarks come in 6 types. The beauty quark, also called the bottom quark, is one of the heavier varieties. The strange quark is lighter. In the standard model, a beauty quark can transform into a strange quark, but not directly. It has to go through a loop. A virtual particle mediates the process, appears briefly, and vanishes. That loop is what the Feynman diagram traces. That loop is what looks like a penguin, and that loop is why this measurement matters at all. The rarity is not incidental, it is the entire point. In the standard model, only 1 in every million B mesons, particles containing a beauty quark, will decay through this channel. That extreme rarity makes the process extraordinarily sensitive. Think of it this way. If something unknown is exerting an influence on particle physics at a deep level, that influence will be buried inside ordinary high-rate processes where enormous natural signal overwhelms anything subtle. But in a process this rare, the standard model contribution is so small that even a slight nudge from an unknown particle becomes visible. The signal is weak enough that interference shows up. Penguin decays are not just rare. They are a precision instrument built by nature to detect exactly the kind of new physics the LHC was designed to find. That sensitivity is why William Barter, a particle physicist at the University of Edinburgh, described the recent result as, and I am quoting directly, among the most significant results of the last few years at the LHC. He works on the LHCb experiment. He knows what the data looks like, and that is what he said about it. Here is what the data actually showed. Between 2011 and 2018, the LHCb detector recorded 650 billion B meson decays. Not millions, billions. Researchers pulled the penguin decays from that sample and measured their properties with precision that required years of analysis. The result deviated from what the standard model predicts by 4 standard deviations. 4 sigma. What does that mean in practice? Standard deviations measure the gap between what you observed and what chance variation around a true value should produce. 1 sigma is noise, 2 sigma gets attention, 3 sigma is worth a paper, 5 sigma is the threshold the field defines as a confirmed discovery, the point where the probability of a random fluctuation producing that result drops below 1 in 3.5 million. 4 sigma sits below that threshold, but not comfortably below it. At 4 sigma, there is a 1 in 16,000 chance this is a random fluctuation. Those are not reassuring odds. They are not dismissible odds either. This is the specific territory that makes physicists uncomfortable, too significant to ignore, not yet significant enough to force a consensus. And the LHCb experiment has recorded 3 times as many B mesons since 2018. That data has not been fully analyzed yet, which means the number 4 sigma is not the final answer. It is the current answer, with more data sitting in storage. Now consider what 4 sigma in this particular channel actually implies. The loop mediating the beauty to strange transition is sensitive to heavy particles that the LHC cannot produce directly. If those particles exist, leptoquarks, heavier analogues of known particles, any of the candidates theorists have proposed, they can appear inside the loop as virtual contributions and shift the measured rate. The 4 sigma deviation is not a loud anomaly in a high-rate process. It is a precise measurement of a rare process coming back wrong by a margin that has a 1 in 16,000 chance of being nothing. The distinction matters. This is not background noise behaving strangely. This is a signal tuned to sensitivity, and it is pointing somewhere the standard model does not go. What did the broader physics community do with this? The paper was published. It was covered in specialist media. Other physicists cited it, noted the tension with theoretical predictions, and continued their work. The result is real, the significance is real, and the field is watching carefully for what the next round of data produces. That response is reasonable given that the gold standard threshold has not been crossed. What did the broader public conversation do with it? Nothing. A deviation with a 1 in 16,000 chance of being random, described by a working physicist as among the most significant recent results at the most powerful particle accelerator ever built, received a fraction of the attention of any number of announcements that carried far less evidentiary weight. And then the broader world moved on, which is exactly what happened with every other uncomfortable result in this story. In February 2026, CERN recreated the conditions of the universe as it existed a fraction of a second after the Big Bang, and what they found inside does not match the picture that has appeared in textbooks for 50 years. The experiment involved colliding heavy atomic nuclei at energies sufficient to dissolve the boundaries between individual particles. At those temperatures, roughly 100,000 times hotter than the core of the Sun, protons and neutrons stop existing as distinct objects. The quarks and gluons that make them up come apart and move freely, no longer bound to each other. What you get is quark-gluon plasma. It is not a gas, not a solid, not a conventional liquid. It is the state of matter the entire universe occupied in the first microseconds after the Big Bang, before things had cooled enough for quarks to bind into anything recognizable. MIT's Yenjie Li described the patterns that emerged as splashes and swirls. That description is precise. The plasma did not explode outward in chaotic fragments. It flowed. It moved the way a near-perfect liquid moves, coherent, organized, with fluid dynamics that matched hydrodynamic models rather than models of high-energy particle scattering. Here is why that result is disorienting. Ask any educated adult how the universe began, and the word they reach for is explosion. The Big Bang. The name itself implies violent, outward, chaotic release. Every illustration, every documentary, every textbook entry for 50 years has framed it that way. The physics is now saying something different. In the moments immediately following the Big Bang, the universe was not exploding. It was flowing. It was a liquid. And the difference between those two things is not a matter of metaphor or emphasis. Explosion and liquid are physically incompatible descriptions of the same event. They carry different equations, different predictions, different implications for what the universe looked like as it expanded and cooled. Getting that wrong for 50 years is not a minor calibration error. It changes the model from which cosmologists have been working. What quark-gluon plasma actually behaves like matters enormously. A perfect liquid has essentially zero viscosity. It resists flow as little as the laws of physics allow. The quark-gluon plasma produced at CERN came closer to that limit than any other material ever measured, including superfluid helium. That is not a background detail. It tells you something about the fundamental interactions between quarks and gluons under extreme conditions. Interactions that fed directly into how the early universe structured itself as it cooled. If the primordial soup was more ordered than expected, then the sequence of events that followed, the formation of protons, of hydrogen, of the first light elements, requires a revised starting point. Cosmologists build their simulations from initial conditions. Change the initial conditions, and the simulation produces a different universe. This is a pattern worth registering now because it will appear again. CERN does not regularly produce results that require physicists to update a single parameter in an existing equation. It produces results that require physicists to ask whether the conceptual framework the equation was written inside is the right framework. The penguin decay anomaly is not a question about a specific rate. It is a question about whether the standard model's accounting of what influences rare decays is complete. The quark-gluon plasma result is not a question about a specific temperature measurement. It is a question about whether the most basic narrative cosmology tells about the universe's origin is accurate. These are different categories of revision. One is a number that changes, the other is a picture that changes. The practical problem is that pictures are harder to change than numbers. A researcher can publish a paper updating a decay rate. Updating the foundational description of the Big Bang means revising how cosmology is taught, how models are structured, and which assumptions are safe to carry forward into the next generation of simulations. The institutions built to manage scientific knowledge move more slowly than the data that accumulates inside them. That gap between what the experiments are producing and what the established frameworks have absorbed is where the real story of modern physics lives. The universe, in its first instance, moved like a liquid. It had viscosity approaching zero, fluid dynamics that matched hydrodynamic models, and internal coherence that no explosion model predicts. That result is in the published literature. It has been confirmed. The textbooks have not caught up with it. The universe did not begin as an explosion. There should be nothing. Not stars, not planets, not atoms, not empty space with occasional rocks floating through it. Nothing. The mathematics of the Big Bang is clear on this. When the universe began, it produced matter and antimatter in equal quantities. Every particle of matter had a corresponding antiparticle, identical in mass, opposite in charge, and when the two met, they annihilated each other completely. energy out, nothing left. By any straightforward reading of the physics, that process should have run to completion in the first seconds of the universe's existence. The matter and antimatter should have cancelled, and the universe should have collapsed back into radiation with no structure left to speak of. Instead, there are 2 trillion galaxies. That discrepancy is not a footnote. It is the most fundamental unanswered question in physics, because it is not asking why the universe has this property or that property. It is asking why the universe exists at all rather than not existing. The standard model has no complete answer. The best the theory can offer is that there must be some asymmetry, some subtle difference in the behavior of matter and antimatter that allowed a small excess of matter to survive the annihilation and become everything that now exists. 1 part in a billion, roughly. For every billion antiparticles produced, 1,000,000,001 matter particles, and that 1 in a billion surplus is the entire observable universe. Galaxies, stars, planets, the 8.1 billion humans alive right now, all of it built from what was left over. The theory acknowledges this asymmetry must exist. It does not tell you why. So, physicists call this problem CP violation, shorthand for a set of symmetry breakdowns that distinguish matter from antimatter at the fundamental level. Some CP violation has been observed in experiments, nowhere near enough to explain the universe. The gap between the measured asymmetry and the one required to produce a matter-dominated cosmos is enormous. Something is missing from the picture, and the field has known it for decades. What it has not had until recently is the ability to study antiprotons with the precision the question requires. Producing antiprotons is one problem. Holding them is another. Antimatter cannot touch ordinary matter without annihilating, which means every container, every instrument, every surface in the experimental setup is a threat. The technical challenge is not metaphorical. CERN's antiproton decelerator has been producing and trapping antiprotons for years. The base experiment, running at the facility, has made some of the most precise measurements of antiproton properties ever recorded. But there are measurements the antiproton decelerator cannot perform. Measurements that require different instruments, different environments, different experimental setups at other facilities entirely. The antiprotons have to move. For a long time, that was simply not possible. Antimatter does not travel well. In 2025, the BASE collaboration announced a result that looks, on its surface, like a logistics achievement. They successfully transported a magnetic trap containing 92 antiprotons across the CERN campus. The trap held. The antiprotons survived. It was the first time this had ever been done. A magnetic bottle of antimatter moved physically from one location to another, arriving intact. What that actually represents is the first time in history that antiprotons produced at the world's leading antimatter facility could be delivered to a different laboratory for measurements the source facility could not provide. The pipeline that physicists have needed for decades now exists. Why does it matter whether you can move the antiprotons? Because the asymmetry question is ultimately a measurement question. If protons and antiprotons are perfectly mirror images, then the standard model's failure to explain the matter-antimatter imbalance is a deep theoretical problem with no obvious experimental path forward. But if antiprotons behave differently from protons in measurable ways, if the mirror is not quite perfect, if there are subtle differences in their magnetic properties or their charge-to-mass ratios that existing instruments at the antiproton decelerator were too imprecise to detect, then the explanation for the asymmetry may already be in the data, waiting for an instrument sensitive enough to see it. The specialized facilities that antiprotons can now reach are built for exactly that precision. 1 part in a billion is the surplus that built the universe. Physicists are trying to measure differences that may be smaller than that. The scale of what is being attempted here is worth sitting with. The tools to pursue that measurement have just, for the first time, become available. The answer to why anything exists at all may be sitting in the difference between a proton and its mirror image, and for the first time, physicists can actually move that mirror image to a place where they can look at it properly. For more than 20 years, a particle called the Xi existed only as a debate. Earlier experiments had claimed to observe it. Those claims were never confirmed. Other experiments looked and found nothing. The particle sat in theoretical models as something that had to exist, a doubly charmed baryon, heavier cousin of the proton, built from 2 charm quarks and 1 up quark, waiting for an instrument precise enough to settle the argument. The upgraded LHCb detector at CERN settled it. The particle is real. Its mass matches theoretical predictions with reasonable precision, though it does not match the earlier disputed claim that started the argument in the first place. That discrepancy between what the earlier experiment thought it saw and what the confirmed mass actually is matters. It means 2 decades of unresolved debate were not about whether the particle existed, they were about whether anyone had actually measured it correctly. What makes the XCC Plus significant is not just its existence, it is what it tests. The strong nuclear force is what binds quarks together inside particles like protons and neutrons, and inside more exotic structures like this one. The theory of how that binding works, quantum chromodynamics, is well established. It makes predictions. The KEXCC Plus is the kind of particle where those predictions become testable in a new regime, 2 heavy charm quarks held together inside a single baryon, a configuration that probes the strong force in conditions that ordinary protons and neutrons never expose. The measurement confirms the framework in broad terms. In fine terms, the numbers come back slightly off. Not dramatically. Not enough to claim the theory is wrong. Enough to note it, cite it, and file it alongside the other measurements that come back slightly off. Then there is the BC plus meson, presented at the LHCb Physics 2026 conference, a composite particle containing 1 charm quark and 1 bottom antiquark, bound together by the strong force. Mesons made from heavy quarks like these are among the most useful probes of quantum chromodynamics, precisely because the interactions are complex and the theoretical predictions require pushing the mathematics hard. The peak in the data when the BC Plus was observed exceeded 8 standard deviations. That is not an anomaly, that is not a hint. 8 sigma is a discovery by any standard particle physics uses, more than 3 times the threshold required for a formal discovery claim. The particle was not in dispute, it was simply unobserved. Now it is observed, and its measured mass lands within the range of theoretical expectations, though slightly deviating from the most precise recent calculations. Both particles existed on paper before they existed in a detector. That is how particle physics works at this level. The theory predicts the structure, the experimentalists build the instrument capable of finding it, the instrument finds it, and the measurement either confirms the prediction or it does not quite. In these 2 cases, it does not quite. The deviations are real, they are within uncertainties, and that phrase, within uncertainties, is doing a great deal of work in the published literature right now. Every measurement has uncertainty. The question is whether the small consistent gap between prediction and measurement, replicated across different particles, different detection methods, different experimental teams, represents noise or signal. The individual cases do not answer that question. The accumulation of them is starting to. What you are watching is the theory being stress-tested from every direction simultaneously. Each new particle is a new test. Each test that comes back exactly right strengthens the model. Each test that comes back slightly wrong is a data point. 1 data point is nothing. 10 data points pointing the same direction is something worth paying attention to. The GCC Plus and the BC Plus are 2 more entries in a list of measurements that the standard model almost explains. Almost is the critical word. It has been the critical word for long enough now that the field cannot keep treating it as a rounding error. 2 particles confirmed in the space of a few years, both slightly off from the theory, and the theory has been slightly off from reality for long enough now that the word slightly is starting to lose its reassuring quality. Gravity is the force every human being has felt every moment of their life, and the standard model, the most comprehensive theory of fundamental physics ever constructed, does not include it. That is not a minor omission. The standard model accounts for electromagnetism, the strong nuclear force, and the weak nuclear force. It describes how those forces operate through the exchange of force-carrying particles, photons carrying electromagnetism, gluons carrying the strong force, W and Z bosons carrying the weak force. The framework is extraordinarily precise. It has predicted experimental results to better than 1 part in a billion. And then there is gravity, No carrier particle, no mechanism, no place in the equations. The force that structures every galaxy, every solar system, every orbit of every planet is simply absent from the most complete description of physical reality that physics has ever produced. General relativity explains why. Einstein's framework describes gravity not as a force in the conventional sense, but as geometry. Mass curves space-time. Objects follow the curvature. What you experience as gravitational attraction is actually the shape of the space you are moving through. This is not metaphor. The mathematics is precise, the predictions confirmed across a century of observation. Gravitational waves, the bending of light around massive objects, the precise behavior of GPS satellites which require relativistic corrections to function. General relativity works. The problem is that it is mathematically incompatible with quantum mechanics. Put the two frameworks in the same equation at the scales where both should apply, and you get infinities, not large numbers, infinities. The calculation breaks down compl. Telly. This is not a matter of needing better data, it is a structural failure in the foundations. So, what is gravity actually? That question sounds simple. It is not. At the quantum level, forces are mediated by particles. If gravity is a force in that same sense, there should be a carrier particle, the graviton. Theorists have described what it should look like. It should have no mass, no electrical charge, and a spin of 2. Nobody has ever detected one. The graviton remains entirely theoretical, and the reason no experiment has detected it is not a limitation of current instruments. The gravitational force is so weak relative to the other three forces that detecting a single graviton would require a detector the size of Jupiter, operating for geological timescales. This is not an engineering problem we can solve with better technology. The weakness of gravity is itself one of the pest unsolved problems in physics. Why is gravity so much weaker than the other forces? By a factor of roughly 10 to the power of 36. That number has no explanation. The standard model offers none. So here is where the recent anomalies become relevant. The penguin decay deviations, the quark mass measurements that come back slightly wrong, the top quark associations that no one predicted. These are not problems in some peripheral corner of the theory. They are problems at the boundary between what the standard model describes and what lies beneath it. Every theoretical framework proposed to extend the standard model, supersymmetry, leptoquark models, extra dimensions, was designed in part to address the gravity problem. Supersymmetry, for instance, provides a mathematical structure that makes unification of all four forces more tractable. If the LHCb anomalies point toward new physics, the new physics they point toward is almost certainly physics that also speaks to gravity's absence. From the current framework, the incompatibility between general relativity and quantum mechanics tells you something specific. It tells you that both theories, despite their extraordinary precision in their respective domains, are approximations. Somewhere at scales smaller than anything the LHC can currently probe, both break down. The true underlying framework, whatever it is, has to reproduce quantum mechanics at quantum scales and general relativity at cosmological scales while being neither of them at the deepest level. What that framework looks like is completely unknown. String theory has been the dominant candidate for decades. It has not produced a testable prediction that experiments have confirmed. Loop quantum gravity is another candidate. It has its own unresolved problems. The honest position is that nobody knows what a complete theory of physics looks like, and the anomalies accumulating at CERN are the closest thing to an experimental signal pointing toward where to look. The theory that describes everything else has nothing to say about the force that holds you to the ground, and after 50 years of trying, nobody has made that problem go away. Fabiola Gianotti, the Director General of CERN, said it directly: 95% of the universe is still unknown. That is not a rhetorical flourish. That is a precise accounting of what the standard model actually covers. Every particle the model describes, every quark, every lepton, every force-carrying boson, every interaction that any detector on Earth has ever measured, all of it adds up to roughly 5% of the total mass-energy content of the universe. The other 95% has no entry in the model, no mechanism, no particle, no mathematical term. It is not that the model gets those components approximately right, and physicists are working on the precision. The model does not address them at all. What does that tell you about a theory that physicists describe as the most successful in the history of science? Break the 95% into its two components, and both of them become harder to look at, not easier. Dark matter accounts for approximately 27%. It does not emit light. It does not absorb light. No instrument designed to detect standard model particles has ever registered it directly. What physicists know about dark matter comes entirely from its gravitational effects on the things they can see. Galaxies rotate. When you measure the stars at the outer edges of a spiral galaxy, they move too fast, far too fast. If only the visible mass were present, the outer stars would fly off into space. They do not fly off. Something is holding them there, something with mass, distributed in a halo around the galaxy, exerting gravitational pull on every star in the structure. That something has no name in the standard model. It has no particle assigned to it. It is just missing mass, noted, discussed in thousands of papers, and officially unexplained for decades. Dark energy is a different problem, and in some ways, a stranger one. In 1998, two independent research teams measuring the brightness of distant supernova found something neither team was looking for. The expansion of the universe is not slowing down. It is accelerating. Galaxies are moving apart from each other faster now than they were a billion years ago, and faster a billion years ago than 2 billion years ago. Something is pushing the universe outward at increasing speed. That something is called dark energy. It constitutes roughly 68% of the total mass energy content of everything that exists. And the standard model has nothing to say about what it is, where it comes from, or why it operates at the scale it does. The best theoretical estimate physicists can produce for the energy density of empty space differs from the measured value by a factor of 10 to the power of 120. That is not a rounding error. That is the largest discrepancy between a theoretical prediction and an experimental measurement in the history of science. Now consider the framing. When physicists describe the standard model, the word that comes up most often is precision. Predictions confirmed to 10 decimal places. Experimental results matching theory to extraordinary accuracy. And that description is accurate for the 5%. Within that narrow slice of reality, the model works with a precision no other scientific theory has matched. But precision within a domain is not the same as completeness. A map that describes 5% of a continent with perfect accuracy is still a map of 5% of a continent. The remaining 95% is not slightly charted or approximately described. It is blank. Physicists know it is there. The gravitational evidence for dark matter has been accumulating since the 1930s. The evidence for dark energy has been accumulating for nearly 30 years. The model has not incorporated either one, not because the problem is new, but because there is no way to incorporate them without going outside the framework entirely. This is worth sitting with before the next result from CERN gets filed under incremental progress. The anomalies in penguin decays, the unexpected behavior of the quark gluon plasma, the gravity problem that 50 years of effort has not resolved. These are cracks in the 5%. The other 95% is not cracked. It has never been touched. The standard model is not a nearly complete theory of everything. It is a complete theory of almost nothing. When a result deviating from theory by 4 standard deviations appears in particle physics, the field does something very specific with it. It acknowledges the result. It cites the result. Papers reference it carefully, with appropriate qualifications about statistical thresholds and the need for further data. And then the field continues building on the standard model as though the result is a footnote rather than a signal. The 4 sigma penguin anomaly was described by William Barter, a particle physicist at the University of Edinburgh, as among the most significant results of the last few years at the LHC. That sentence appeared in coverage that received a fraction of the public attention of a celebrity physics announcement. What does that asymmetry tell you? This is not a new pattern. Look at the PETM research, a carbon fingerprint pointing at biological origin, a volume no natural source fully explains, 30 years of published literature acknowledging the gap in footnotes and then moving on. Look at the Younger Dryas impact hypothesis, a layer of platinum group elements and shocked quartz appearing at exactly the boundary where a major climate disruption begins, formal papers published, and then a decade of institutional resistance before the question received serious engagement. Look at the Silurian hypothesis. two credentialed researchers published a formal technical model. The field covered it, noted it, and produced no follow-up research programs. 7 years without response from the organizations most capable of investigating it. These are not identical situations, but they share a structure. Uncomfortable data appears. It gets acknowledged. It does not get pursued. That pattern has a name. It is not conspiracy. It is structural inertia. Here is why the inertia exists. The Standard Model is not just a theory, it is an infrastructure. 50 years of experimental physics has been built on the assumption that the model is essentially correct and that what remains is refinement, measuring the Higgs more precisely, constraining supersymmetry, narrowing the parameters. Careers are built inside that assumption. Institutions are organized around it. Funding frameworks are designed to support it. When a result arrives suggesting that refinement is not what is needed, that the foundation itself may require replacement, the professional ecosystem around the model does not update automatically. It resists, and the resistance is rational from inside the system. Consider the incentive structure directly. A physicist who looks at the penguin anomaly, at the top quark behavior, at the quark gluon plasma result, and says publicly that the Standard Model is broken, what happens to that physicist if the anomaly turns out to be statistical noise? Their credibility takes a permanent hit. The field remembers. Funding becomes harder to secure. Collaborations become harder to join. None of that happens to the physicist who stayed cautious. The asymmetry is not subtle. It is the entire operating logic of how scientific careers survive contact with disruptive data. So what you get is careful language. Results are described as tensions rather than failures. Deviations are framed as requiring additional data rather than as evidence of a structural problem. The 4 sigma result sits in the literature. It is real. It is cited. It is not the organizing principle of a field-wide response, which is what it would be if a 4 sigma deviation appeared in a domain where the careers staked on the prevailing theory were fewer. Here is what that tells you about the question the field is actually afraid to ask. It is not whether the Standard Model will eventually need updating. Everyone agrees it will. The question the data is actually generating, whether the anomalies already in the published record are pointing at something that cannot be absorbed by refinement. That question does not get asked directly because directly asking it and being wrong costs everything. Being cautious costs nothing. The structure of the incentive is the structure of the silence. This is worth sitting with. Not as an indictment of any individual physicist, none of whom invented this situation, but as a description of how fields handle results that threaten their foundations. The geological record literature and the particle physics literature produce the same pattern under the same conditions for the same reason. The professional cost of being the scientist who said the Standard Model is broken and turned out to be wrong is asymmetric in exactly the same way it has always been asymmetric, in particle physics and in geology and in every field where the uncomfortable conclusion is also the correct one. The most important word in physics right now is leptoquark, and almost nobody outside the field has heard it. Here is what a leptoquark is. The Standard Model divides matter particles into 2 distinct categories: quarks, which build protons and neutrons, and leptons, which include electrons and neutrinos. These 2 families do not interact directly. The model treats them as separate. A leptoquark is a particle that would bridge that separation, carrying properties of both, capable of interacting with either type of matter. If leptoquarks exist, they would not need to be created directly at the LHC to leave evidence of themselves. Penguin decays are uniquely sensitive to particles that cannot be produced at current collision energies. A leptoquark heavy enough to escape direct detection could still exert a measurable pull on a beauty quark, transforming into a strange quark, bending the decay rate away from what the Standard Model predicts, by exactly the kind of margin the LHCb data is showing. 4 standard deviations, 1 in 16,000 probability of being random noise. That is not a coincidence that deserves a footnote. That is a signal that deserves a research program. Leptoquarks are not the only candidate. A second category of explanation involves heavier analogues of particles already in the Standard Model. The logic is straightforward. What if the known particles are not unique, but are the lightest members of larger families? Heavier versions at higher energy scales would be invisible to direct production at the LHC, but would still influence rare processes through quantum effects. Their existence would produce exactly what is being observed, systematic deviations from standard model predictions in processes sensitive enough to detect indirect influence. The LHCb penguin measurement fits this pattern. So do several other anomalies distributed across the experimental program. None of them, individually, close the case. Together, they constrain what the new physics can look like and direct future searches toward specific energy ranges and particle types. Then there is supersymmetry. This is the largest and most thoroughly developed theoretical framework waiting beyond the standard model. Supersymmetry predicts a partner particle for every known particle. Every quark has a squark. Every lepton has a slepton. Every boson has a corresponding fermion. The particle count doubles. The theory is mathematically elegant, and it solves several problems simultaneously. It provides a candidate for dark matter. It stabilizes the Higgs boson mass against quantum corrections that would otherwise push it to implausible values. It points toward unification of forces at high energies. The LHC was built partly to find these particles. It has not found them, not in the energy ranges where the simplest versions of the theory place them. That absence is a result. The simplest supersymmetric models are under serious pressure. But absence at one energy range is not absence everywhere, and the theoretical framework has enough flexibility to survive by shifting predictions to higher scales. What the LHC has not done is rule supersymmetry out. It has ruled out specific versions of it. The question of what lives at higher energies remains open. What does that tell you? The field has three serious theoretical candidates for what is producing the anomalies. It has no confirmed detection of any of them, and it has a long history of exactly this situation resolving in favor of the indirect evidence. Radioactivity was discovered in 1896. The W boson, the particle actually responsible for the weak nuclear force processes underlying radioactive decay, was not directly observed until 1983. 80 years of understanding a phenomenon through its effects before the mechanism was confirmed in a detector. The same pattern runs through the history of physics at its deepest levels. The top quark was inferred from indirect evidence years before it was produced directly. The Higgs boson was theorized in 1964 and confirmed in 2012. Physicists knew what the fingerprint looked like long before they could put the particle in a beam. The current situation is not unprecedented. It is actually the normal condition of physics operating near the edge of what current instruments can reach. The fingerprints of something new are appearing in the data. The particle leaving those fingerprints has not been created directly. That is not a failure of the experimental program. That is the experimental program working exactly as it has always worked, at every boundary physics has ever crossed. Indirect observation is how physics has always worked at its deepest levels, and the indirect observations are accumulating. On March 7, 2026, CERN declared stable beams for the final data-taking run before the most significant upgrade in the Large Hadron Collider's history. That phrase, final data-taking run, is worth stopping on, not because the machine is shutting down, because what comes after it is a different machine in almost every sense that matters, running at a scale that makes the current LHC look like a prototype. The upgrade is called the High Luminosity LHC. It begins around 2030. The core promise is an order of magnitude more data than all previous runs combined. Not a refinement, not a percentage improvement. 10 times the collision data produced through upgraded magnets, improved beam focusing, and detector systems rebuilt from the ground up. The Atlas detector alone is getting a completely new inner tracker, a high granularity timing system, and a rebuilt trigger architecture. These are not incremental changes. They are the kind of changes you make when the old instrument has reached the limit of what it can resolve and the questions still have not been answered. Now put that alongside the number that matters most right now. The dataset the LHCb experiment used to find the 4 sigma penguin anomaly covered 650 billion B meson decays. That is the number behind the 1 in 16,000 chance. That is the number behind the most significant result in recent LHC history by the field's own description. Since that dataset was collected, the upgraded LHCb detector has recorded 3 times that many decays. 3 times the original dataset is already sitting in the analysis pipeline. The HLLHC will produce 15 times the current total. So ask yourself what the 4 sigma result becomes when you feed 15 times more data into the same analysis. 2 things can happen. Either the anomaly shrinks, The deviation from theory was a statistical fluctuation, and additional data pushes it back toward the expected value. The standard model holds, the field exhales, or the anomaly grows. The deviation was real, and additional data pushes it past 5 sigma, which is the threshold at which particle physics officially calls something a discovery. At 4 sigma, there is room to be careful. At 5 sigma, there is not. 5 sigma is the line the field drew to protect itself from premature conclusions, and crossing it with a result that directly contradicts the standard model is not a small event. It is an announcement that the framework needs to change. What does that actually mean in practice? 5 sigma on the penguin anomaly means an unknown particle or force is influencing the decay of beauty quarks in ways the standard model does not predict or permit. It means something exists at energy scales the LHC cannot directly access that is still leaving measurable fingerprints in rare processes. It means leptoquarks, or heavier analogues of known particles, or something theorists have not yet named, are not hypothetical candidates anymore. They are conclusions. And every other anomaly in the current dataset, the top quark behavior, the mass measurements that come back slightly wrong, the quark gluon plasma that behaves like a liquid, gets reread in that light. None of them exist in isolation once the anchor anomaly has a 5 sigma conformation attached to it. The field is not there yet. 4 sigma is not 5 sigma. The current data is not the HLLHC data. There is a real and non-trivial chance that the anomaly is statistical noise and the standard model survives this round of scrutiny the way it has survived every previous round. That outcome is also informative. It means the model is more robust than its internal contradictions suggest, and the search for what lies beyond it has to look somewhere else. Both outcomes close something. One closes the question about this specific deviation. The other closes the question of whether the model is complete, permanently, with an answer that the field has been structurally avoiding for a generation. Here is my position on how to read the upgrade program. You do not spend billions of dollars and the coordinated effort of more than 1,000 researchers across 20 countries to build a machine 15 times more powerful than the one that just produced a 4 sigma anomaly if you think the anomaly is probably nothing. The investment is itself a signal, and the data it generates will be the most consequential data in particle physics in 50 years, in one direction or the other. Within the next several years, the LHCb experiment will either have enough data to kill the anomaly or enough data to confirm it, and confirmation means that the theory particle physics has built its entire framework on for 50 years is not the final answer. Neutrinos are the most abundant massive particles in the universe, and for most of physics history, the honest description of how to detect one was essentially this: you cannot. Right now, approximately 65 billion neutrinos from the Sun are passing through every square centimeter of your body every second. They carry almost no mass. They carry no electrical charge. The weak nuclear force is the only force they respond to, and the weak nuclear force is extraordinarily short-range. A neutrino can pass through a light year of solid lead with a better than even chance of emerging undisturbed on the other side. This is not poetic exaggeration. That is the actual physics. The instruments built to catch them are enormous water tanks buried deep underground, surrounded by thousands of sensors waiting for the rare occasion when one neutrino, out of the vast stream passing through, actually strikes something. Detection rates are measured in events per day, sometimes per week. These are not particles that cooperate with measurement, which is why, for decades, physicists working at the LHC took it as given that neutrinos produced inside the collider's high-energy proton collisions could not be directly detected. The collision environment is violent. The signal would be vanishingly small. The background noise from every other particle produced in those same collisions would bury whatever neutrino signal existed. The technical consensus was that it simply was not worth attempting. A team attempted it anyway, and they detected neutrinos at a particle collider for the first time. The result was published, confirmed, and marked a genuine milestone in experimental physics. Not because neutrinos were a mystery, they were not, but because the method opened something new. Neutrinos produced in cosmic rays or in nuclear reactors come from sources that are difficult to characterize precisely. Their energies are distributed across a wide range. Their origin involves processes that introduce uncertainties. LHC neutrinos are different. They are produced in controlled, well-characterized proton-proton collisions at known energies, which means they can be studied with a precision that reactor or solar neutrino experiments cannot match. That is a new experimental window, and new windows in particle physics have a reliable history of showing things the theory did not anticipate. Here is what the theory did not anticipate. The original standard model treated neutrinos as massless. This was not an assumption made carelessly. It followed from the structure of the model itself. The mathematical framework predicted neutrinos with no mass, and for decades every available experiment was consistent with that prediction. Then experiments measuring neutrinos produced in the atmosphere and in the sun found something the model said was impossible. Neutrinos were oscillating, switching between their three distinct types as they traveled. Quantum mechanics is unambiguous on this point. Oscillation between types requires mass. Massless particles cannot do it. The experiments were not wrong. The model was. The revision came. Physicists incorporated neutrino mass into the standard model through a set of additional terms that the original framework did not require. The discovery earned a Nobel Prize in 2015, and the field largely treated it as a successful update to an otherwise sound theory rather than as a demonstration that the model's foundational structure had made a concrete, testable, falsifiable prediction about one of the most abundant particles in the universe and gotten it wrong. That framing matters, because the pattern it represents, anomaly appears, theory absorbs it, field moves forward without fully accounting for what the absorption means, is the same pattern appearing now in penguin decays, in quark-gluon plasma behavior, in top quark associations. Each individual result gets explained. The explanations accumulate, and the question of what it means that the explanations keep being necessary does not get asked with the urgency the data suggests it should. The original standard model said neutrinos had no mass. The experiments showed they did, and the revision that followed was presented as a minor update to a robust theory rather than what it actually was. Evidence that the theory had been wrong about one of the most abundant particles in existence. The top quark is the heaviest fundamental particle ever observed, and it lives for approximately 1/10 trillionth of a second before disintegrating into lighter particles. That is not a rounding error, that is the actual lifespan. It decays before it combined with other quarks to form composite particles, which makes it unlike almost anything else in the standard model. You study it entirely through its decay products, through what it leaves behind, and what the ATLAS and CMS experiments have been finding in those decay products does not match what the model predicts. Both collaborations observed top quarks forming brief, unexpected associations with each other, fleeting pairings that the standard model does not call for. The ATLAS collaboration ran a comprehensive analysis using effective field theory, a framework that lets you set systematic limits on new physics effects without committing to a specific theory of what that new physics actually is. The result was the most complete set of constraints on top quark behavior ever published, and the behavior still came back strange. Now consider what the top quark's mass actually is, roughly 175 times the mass of a proton. The next heaviest quark, the bottom quark, sits at about 4.5 times the proton mass. There is no clean theoretical reason for that gap. The standard model accommodates the top quark's mass. It does not predict it, it accommodates it, which is a meaningful distinction. A theory that predicts a value gives you something to test. A theory that accepts whatever value you hand it tells you less. The top quark's mass sits in a range that theorists building extensions of the standard model find notable. Supersymmetric frameworks, models involving new heavy particles, several of the candidate theories designed to explain dark matter, they all have something to say about mass values near that range. That is not proof of anything, but it is a reason to look carefully at what the top quark is doing. What it appears to be doing is responding to something the model does not include. The unexpected pairings are not large effects. They are not 4 sigma deviations on their own. They are the kind of result that gets carefully noted in the literature and then sits there, waiting for more data, waiting for the theoretical framework that would explain it. What they are not is predicted. The standard model does not produce those associations. Something is influencing the heaviest particle in the known zoo in ways the best theory in physics does not account for, and the honest position is that nobody currently knows what that something is. Here is where it is worth stepping back, because this section of the story could be told in isolation and made to sound like a minor technical discrepancy at the edge of measurement precision. It is not a minor technical discrepancy. Put it next to the penguin decay anomaly, 4 sigma from standard model predictions, 1 in 16,000 odds of being a random fluctuation. Put it next to the quark-gluon plasma that behaved like a near-perfect liquid instead of an explosion. Put it next to the new particles whose measured masses came back slightly off from theoretical values. You now have unexpected behavior spread across multiple particle types, multiple experiments, multiple detection methods. Penguin decays involve beauty quarks transforming into strange quarks. Quark-gluon plasma involves the fundamental state of matter before quarks bound together at all. New particle masses test how the strong force binds constituents together. Top quark associations test the heaviest end of the quark spectrum. These are not the same measurement repeated. They are independent probes of different corners of the same theory, and they are all showing something the theory did not anticipate. Each anomaly has a separate explanation, and the explanations are all technically valid, and together they are starting to look less like a series of small problems and more like a single large one. Every time physics has found a crack in the dominant framework and followed it down, what it found on the other side was stranger than what it left behind. That is not a rhetorical point. It is the actual historical record. Newton described gravity as a force acting at a distance and gave us equations that worked for 2 centuries. They predicted planetary orbits with precision that seemed definitive. Engineers built bridges and artillery trajectories around them. The framework appeared complete. Then Einstein showed that gravity is not a force at all. It is the curvature of space-time. Mass bends the geometry of the universe, and what we experience as gravitational pull is objects following the straightest possible path through curved space. That is not a refinement of Newton. That is a different picture of reality entirely, and the mathematics required to describe it was nothing a Newtonian physicist would have recognized as physics. Then quantum mechanics arrived, and if relativity stretched what the human mind could hold, quantum mechanics broke the container. Particles that exist in multiple states simultaneously until measured. Probabilities as fundamental descriptions of nature, not as approximations covering ignorance. 2 particles separated by any distance affecting each other instantaneously in ways that cannot be explained by anything traveling between them. Einstein spent the last decades of his life convinced quantum mechanics was incomplete because its implications were too strange to be final. He was wrong. The experiments confirmed it. The strangeness was real. So ask the question plainly. If the standard model is incomplete, if the anomalies in penguin decays, in top quark behavior, in mass measurements that keep coming back slightly wrong are pointing at something real, what is waiting on the other side of it? The honest answer is that nobody knows. But the pattern says it will not be simpler. It will not be more intuitive. It will not look like a modest extension of what already exists. New particles means new force carriers. New force carriers means new interactions between matter that current physics does not account for. And new interactions means phenomena that the existing framework would classify as impossible are not impossible. They are just operating through a mechanism the standard model has no category for. That is not a small adjustment. The forces we know about, electromagnetism, the strong nuclear force, the weak nuclear force, determine which chemical reactions are possible, how atomic nuclei hold together, how stars burn. A new force is a new answer to questions that currently appear settled. The standard model is not describing some peripheral edge case of physical reality. It is describing what matter is made of and how it behaves. When that description turns out to be incomplete, the incompleteness is not in the margins. The anomalies coming out of the LHC are not in exotic corner cases designed to stress test secondary predictions. Penguin decays probe the transformation of one fundamental quark type into another. Top quarks are the heaviest fundamental particles in existence. These are central objects of the theory, not footnotes to it. What does it mean in practice, concretely, for the standard model to break? It means the mathematical structure that physicists have used to calculate and predict the behavior of matter for 50 years is an approximation of something deeper. The same way Newton's equations are an approximation that works at low velocities and ordinary scales, but fails at relativistic speeds and extreme gravity. The approximation is not wrong, it works within its domain, but the domain has edges, and the edges are where the physics lives that the approximation cannot see. The LHC is running at energies high enough to approach those edges, and what it is finding there does not fit. Not dramatically, not yet, not in ways that have crossed the 5 sigma threshold that forces an official reckoning, but consistently, across different experiments, different particles, different detection methods, different research groups. The pattern of not quite fitting is not random, it has a direction. Every previous framework that turned out to be an approximation was replaced by something with more explanatory power and more conceptual strangeness. Classical mechanics was intuitive. Objects move when pushed, stop when resisted. Relativity required you to accept that time passes at different rates depending on velocity. Quantum mechanics required you to accept that the question of where a particle is has no answer until you measure it. Newtonian mechanics was replaced by something that bent time and dissolved the boundary between matter and energy, and the thing that replaced it might be replaced by something that makes those concepts look simple. The proposed future circular collider would be 91 kilometers around, roughly the circumference of a mid-sized city's highway ring, and it would operate at energies 7 times greater than anything the current Large Hadron Collider can reach. 7 times. That is not an incremental upgrade. That is a different machine in a different category of physics, capable of probing energy scales where the particles and forces that current detectors cannot directly produce would become accessible for the first time. The LHC runs at 13 to 14 trillion electron volts. The FCC is designed to reach 100 trillion. At that energy, whatever is hiding behind the anomalies in the penguin decays, whatever is producing the dark matter signatures in galactic rotation curves, whatever is generating the matter matter asymmetry that allowed the universe to exist at all, those things would stop being inferences and become measurable objects. The cost is real. Estimates run into the tens of billions of dollars. The timeline extends across decades. This is not a single government's decision or a single laboratory's budget line. It requires sustained international commitment across a period longer than most political cycles and most institutional planning horizons. That is the honest description of what building it would take. And the question worth asking directly is why, given everything the LHC has shown in the last several years, that commitment is still a debate rather than a settled decision. Here is the scientific argument for the FCC stated plainly. The standard model has 4 open problems that have not closed in 50 years. Gravity is not in the model. Dark matter is not in the model. The matter-antimatter asymmetry has no complete mechanism in the model, and the model is now producing 4 sigma deviations in penguin decay experiments that have a 1 in 16,000 chance of being random fluctuation. If those problems were resolving, if each year brought the gap narrower, the anomalies smaller, the missing 95% of the universe slightly less missing, then the argument for a larger machine would be correspondingly weaker. You do not need a more powerful instrument if the instrument you have is converging on answers. None of those problems are converging. Several are deepening. The scientific argument for the FCC is not ambition. It is the direct response to data that the current machine cannot fully answer. So what does it mean that this is still a debate? The Director General of CERN has stated publicly that 95% of the universe is unknown. That is not a rhetorical flourish. That is the field's own accounting of its own ignorance, stated by the person running the world's premier particle physics facility. And the response from the institutions and governments positioned to act on that assessment has been deliberation, studies, feasibility reports, the careful management of a decision that the data has already made. This is the same asymmetry that appears everywhere in this story. The professional cost of committing to the FCC and having it produce results that incrementally extend the standard model without breaking it is high, politically, financially, institutionally. The cost of waiting is absorbed by no one in particular. It distributes across the entire field as continued ignorance, and continued ignorance has no identifiable author. There is a version of this argument that sounds like impatience, and that is not what this is. The FCC is a multi-decade project. The physicists advocating for it understand the timeline better than anyone. What they are saying is that the decision to begin has to precede the result by 30 years, and the window in which that decision makes sense is now, when the anomalies from the LHC are fresh and the scientific case is at its strongest. Waiting for more certainty before committing to the instrument that would produce that certainty is circular in a way that the field knows and rarely says plainly. The dark matter problem is not a small correction to an otherwise complete picture. The gravity incompatibility is not a footnote. The matter-antimatter asymmetry is the reason matter exists. These are not peripheral questions. They are the questions. And the machine that has the best realistic chance of answering them is sitting in a feasibility study while the anomalies that justify it continue to accumulate in the published literature. The scientific case for building it is written in the anomalies, and the anomalies are not shrinking. Here is what you have by the time you put all of it in the same paragraph. Quark-gluon plasma that behaves like a near-perfect liquid, not a chaotic explosion. A 4 sigma deviation in penguin decays with a 1 in 16,000 chance of being random noise. New particles confirmed at the LHCb detector whose measured masses land slightly outside their theoretical predictions. Top quarks forming brief associations that the standard model does not account for. Neutrinos detected at a particle collider for the first time in history. Antiprotons physically transported across a laboratory campus so they can be compared to protons with a precision that was previously impossible. That is the list. Not one result, not two. 6 distinct experimental findings from different detectors studying different articles using different methods. Each one arrived with its own careful language. Each one was cited, noted, and filed. Now ask yourself what that list looks like if you stop reading each result in isolation and read them as a sequence. The standard model has been tested continuously for 50 years, thousands of experiments, precision measurements down to extraordinary decimal places. It passed every test. That is not a small thing. A theory that survives 50 years of rigorous experimental challenge is not a guess. It is a structure that has earned its credibility through something harder than argument, through prediction after prediction that turned out to be correct. That record is exactly why the current results matter as much as they do. These are not anomalies appearing in a weak theory. They are appearing in the strongest theory physics has ever produced. When cracks show up there, you pay attention to them differently than you would pay attention to cracks in something that was already under suspicion. What would a breaking standard model actually look like in the published literature? Think about that concretely. You would expect to see rare processes deviating from predicted rates because rare processes are where the influence of undiscovered heavy particles would show up first. You would expect to see mass measurements coming back slightly wrong, small enough to be individually dismissible but persistent across multiple particle types. You would expect to see behavior in extreme conditions, like the quark-gluon plasma, that does not match theoretical expectations built on the model's assumptions. You would expect to see experimental capabilities expanding into new territory and finding, each time they expand, something that was not fully anticipated. That is the description. Compare it to what is currently sitting in the published record from the last several years. The comparison is not comfortable. Here is my position on what that means. Each individual result has a technically valid explanation that preserves the model. The penguin deviation could be a fluctuation. The plasma behavior could be an effect the theory accommodates with adjustments. The mass discrepancies are small. Top quark associations are unexpected but not impossible within the existing framework. Every one of those statements is true. And every one of them is also the thing a physicist says when the professional cost of the alternative statement is asymmetric. The data does not require you to conclude the model is breaking. It permits you to avoid that conclusion, at least for now, with careful language about uncertainties and pending confirmation. That option remains available. The question is how long it remains available and whether taking it is the same thing as following the evidence. The probability calculation is not straightforward. These are not independent experiments in the statistical sense that allows you to simply multiply probabilities together. They share infrastructure. They share theoretical assumptions in how results are interpreted. The tests are correlated in ways that make a clean numerical answer impossible. But correlation does not explain the direction. When 6 results all point toward the same gap in the theory, the correlations explain why you cannot multiply probabilities. They do not explain why every result lands on the same side. A random distribution of errors points in random directions. This does not. What the accumulation produces is not a proof. It is a fingerprint, not a fingerprint with a name attached. a fingerprint that keeps appearing in places where the theory said nothing unusual should be happening, across different experiments, across different particle types, across different detection technologies. You can explain each appearance individually. The question the field has not answered directly is what explains all of them simultaneously. When multiple independent experiments at the same facility all produce results pointing in the same direction, the word for that is not coincidence. There is a version of the next 10 years in which the high luminosity LHC generates 15 times the current dataset. The penguin anomaly crosses 5 sigma, and particle physics faces a result it cannot absorb without changing what it thinks it knows. That version is not guaranteed. The anomaly could disappear. More data has killed 4 sigma results before. The standard model has survived every serious challenge thrown at it for 50 years, and statistically, it is allowed to survive this one too. But here is what does not disappear regardless of which way the penguin result resolves. The quark-gluon plasma behaved like a liquid. The new particles came back with masses slightly off from prediction. The top quarks formed associations nobody expected. Neutrinos were detected at a collider for the first time. Antimatter was physically transported to a location where it can finally be compared to matter with real precision. These are not the same result measured 5 different ways. They are 5 different results, from different experiments, using different particles, pointing in the same direction. That does not resolve cleanly no matter what happens to the penguin decay number. What the HLLHC actually does, at its core, is force a decision, not a policy decision, a factual one. The dataset becomes large enough that the statistical argument for caution runs out. Either the signal is real and the field has to say so formally, or the signal was noise and the model gets a reprieve. Both outcomes are informative. One tells you the theory holds at this energy scale and the anomalies were fluctuations. The other tells you the theory has a boundary and something exists on the other side of it. What that something is, nobody knows yet. Leptoquarks are a candidate. Heavier analogues of known particles are a candidate. Supersymmetric partners are a candidate. The data will not come labeled. It will come as numbers, and the numbers will either fit or they will not. Here is my position on the institutional response that follows whichever outcome arrives. If the anomaly disappears, the field will treat this as confirmation of its methods. Careful, rigorous, no overclaiming. If the anomaly crosses 5 sigma, the same institutions that described it as significant but preliminary for years will face the question of why the implications were not pursued more directly when the signal was sitting at 4. The professional caution that made sense at 4 sigma does not produce the same defense at 5. At 5, the result is a discovery, and discoveries require an accounting of what they mean, not just what they measure. The universe ran for 13.8 billion years before producing instruments capable of measuring penguin decays in 650 billion B-Meson collisions. It is not waiting for physicists to find a convenient moment. The matter-antimatter asymmetry that left a universe full of galaxies instead of nothing does not care whether the explanation is compatible with a 50-year-old theoretical framework. Gravity does not become easier to unify with quantum mechanics because the incompatibility is inconvenient. Dark matter does not become detectable because the model that excludes it has a strong publication record. The 95% of the universe that Giannotti described as unknown is not unknown because the experiments have not been run. It is unknown because the theory that guides the experiments does not reach it. What the next 10 years produce depends on what physicists are willing to ask when the data stops being ambiguous, not what they are technically capable of asking. What they are institutionally willing to ask out loud, in print, in funded research programs, in the follow-up studies that currently do not exist for results that point somewhere uncomfortable. The history of this field is a history of frameworks that seemed complete until they weren't. Each one held until the instruments got precise enough to find the edge. The instruments are getting precise enough. The question is not whether the data will keep accumulating. It will. The question is whether the institutions built to interpret it are prepared for what it might say.